Hello, everyone. Welcome to Physics 213, Lab 1. This lab is going to cover several topics. First of all, we'll talk about circular motion, which we'll look at something called a rotational apparatus, and where we calculate the centripetal force. We'll also look at a ball, like a steel marble, rolling over a roller coaster track and a loop track, where we have it set up so that the marble is just ready to leave the surface of the track at a particular point. And we're going to calculate what's called the critical speed of the ball, just when it's ready to leave the track. Then we'll talk a little bit about moment of inertia. We'll calculate the moment of inertia of an aluminum rod or aluminum stick about several different points, several different axes of rotations of that aluminum rod. And then finally, we'll look at a little bit of conservation of angular momentum, where we have a student sitting in a chair, rotating, and then they are either bringing in weights, pulling weights close to their body, or they're rotating a wheel, spinning wheel. It's kind of counterintuitive. I have a video that was recorded several years ago on this, and we will watch that video and at least qualitatively talk about conservation of angular momentum. Okay, so to start, let me go over a little bit of the theory of circular motion. Okay, so I want to start by talking about what's called uniform circular motion. Let's say we have a particle and it's traveling at a constant speed. So at this instant at the top here, let's say it has a velocity vector in this direction. So this is say v1. And then a little time later, let's say it has a velocity in this direction. Right, the velocity vector is always going to be tangential to the path. Remember, it's traveling in a circle. And when I say it's traveling at a constant speed, it means that the magnitude of those velocities is the same, right? It's constant. So the length of v1 and v2 are always going to be equal, right? So remember, the definition for average acceleration, it's equal to change in velocity over change in time. So there's going to be an acceleration if either the magnitude of the velocity changes, right? That would be the case if you had one-dimensional motion, or the direction of the velocity changes, or both. In this case, the magnitude of the velocity is not changing, but the direction of the velocity vector is changing. So we do have an acceleration. Okay, so to figure this out, remember I can write delta V as it really means V final minus V initial. So in this case, I'll call it V2 minus V1, right, over delta V, or sorry, over delta T. And then V2 minus V1, I can write as V2 plus a negative V1, right? When I subtract vectors, it's the same as adding the opposite of that second vector. So what does that look like? Well, in this case, right, if I draw V2, remember V2 looks something like this. So this is V2. V1 was up here, right? So negative V1 is going to be the same length, but it's going to be in opposite direction. So if I add negative V1 to V2, then I want the tail of negative V1 to be at the tip of V2. So it looks like this. So this is really negative V1. So I'm adding here, right? So this is V2 plus negative V1. And that result is going to be delta V. That's my change in velocity. So it's in that direction. So it turns out, and it's hard to see this, I'm sort of just doing this qualitatively here, but it turns out that the direction of delta V is going to be towards the center. And since the average acceleration, right, remember, is equal to delta V over delta T, and delta T is just a scalar, it's just a number. So the direction of the acceleration depends on the direction of delta v, because that's what the vector is, right? So in this case, the acceleration is going to be towards the center. So the acceleration will be directly towards the center. Okay, and that acceleration has a name. It's called the centripetal acceleration. So this is the centripetal acceleration. So whenever a vector is changing direction, and if it's traveling in a circle, right, if the change direction and the path of the object is circular, then there's going to be this centripetal acceleration towards the center of the circle. Now, in lecture, you also learned that it has a magnitude, right? And that magnitude depends on the linear velocity, the tangential velocity, and the radius. So let me just give that to you now. So sometimes you write magnitude as absolute value of A, or you could just say A. I'll just write a little C here to remind you that it's centripetal acceleration. And remember from lecture, it's equal to V squared over R. Right, so that's the magnitude, but the direction is towards the center. Now, we also know how to relate the angular speed or angular velocity to the linear velocity. So if I have, say, a circle again, let me draw it here. And this is my radius. Let's say I want to know the linear or tangential velocity v, and actually I'll just look at the magnitude of it, so I'll just call it v. And I know that the angular velocity or angular speed omega is so many radians per second, then the v here, this tangential or linear velocity, is simply equal to r times omega. Okay, so another way that we can write the magnitude of the centripetal acceleration is instead of v, instead of the linear velocity, I can plug in r omega. And if you work this out, right, this is going to be r squared omega squared over r, and one of the r's will cancel. So another way of writing the centripetal acceleration is simply going to be r omega squared. So you can either write it as v squared over r or r omega squared. In one case, it's written in terms of the linear velocity. In the other case, it's written in terms of the angular velocity or angular speed. Okay, so that brings us to centripetal force. What is the centripetal force? Well, basically, it's the force, it's the net force that causes the centripetal acceleration. Okay, so centripetal force again, it's going to be directed towards the center, right, of the circle. And the way you can think of it is it's the sum of all the forces in the radial direction. And it's equal to ma, right? But the a here is a centripetal acceleration. So I could write this as either mv squared over r. So that's one way of writing it. Or I could write it as m times r omega squared, depending on whether I want to use the linear velocity or the angular velocity. Okay, so that's an important equation. We will need to use this later in the lab. All right, the second thing I want to talk about, and this deals more with the roller coaster track and the loop track. Actually, let me go to a new page here. So let's say we have a curved surface. And we're going to assume it's circular. And in one case, we have the ball rolling on top of it, like a roller coaster. And in the second case, we have the ball rolling underneath. So that would be like the loop. And we want to know what's going on right when it's at the peak of that curve. So first of all, what are the forces acting on the ball at the peak of the curve? Well, we have the weight of the ball, right? And it's going to be like a steel marble in this case. So the weight acts down. And we have a normal force, right, that the surface exerts on the ball perpendicular to the surface. And the way you do that is you draw a tangent line to the surface, and it's perpendicular to that tangent line. So in this case, it'll be straight up. So there's a normal force like this. And you might even, if you're being really careful, there's also what's called a frictional force, and it's a rotational frictional force. But it's acting perpendicular, so it's not going to really affect our calculation. It's acting in this direction, depending on which way the ball is rolling. Okay, so what we want to do is we want to look at the sum of the forces just in the radial direction towards the center of that circle. So I'm going to call this direction right here. I'll do it in red here. This is like my plus R direction. You could say Y if you want. I'm just going to call it R for like radial. Okay, and actually on the other picture, I have the same situation, except here, the weight acts down, right, towards the center of the earth. The normal force also acts down. There could be a rotational frictional force. And again, I'm going to talk about, let's talk about just the radial direction towards the center of the circle. So this will be like plus R. Okay, so now we're going to apply Newton's second law. We're going to look at the sum of the forces in the radial direction, and that's got to equal the mass times the acceleration, but in this case, it's going to be the centripetal acceleration. Okay, so in the roller coaster track, let's see, I have W acting down. Remember I'm calling towards the center positive, so that's going to be positive W. Normal force is acting in the opposite direction, a negative direction in this case, so minus N. And that's got to equal M. And then for the centripetal acceleration, I'm going to write as V squared over R. And then in the second case, I have the weight acting down, so it's positive, plus the normal force is also positive, and that's got to equal mv squared over R. Okay. So here's the key point. And when you watch how I collected the data, so you should definitely watch the video on how I collected the data for this, this situation with the roller coaster track and the loop track. I have the position of the track set so that when the ball rolls over the top here, it's just ready to leave the surface at that instant at the top there. It's just ready to lose contact with the surface. And same thing in this case, when it rolls underneath, it's just ready to fall here, just ready to leave the surface, so to lose contact. So if it's just ready to lose contact with the surface, then what variable can I set equal to 0? What variable can I get rid of? Well, the normal force, right? If it loses contact with the surface, then there's no force that the surface exerts on the ball. So I have this set up so in both cases, the normal force here is going to be 0. So this normal force is 0. Now I can write the weight as mg. So in this case, I'm going to get exactly the same equation. Right? It'll be the same equation in both cases. So notice what happens here. I can cancel the m's. And I want to solve for v. V is going to be called the critical speed, right? Or the critical velocity. It's the speed at which the ball is just ready to leave the surface. So to solve for v here, I'd have to multiply both sides by r. Right? And then take the square root. So you're going to find that v is equal to the square root of r times g. And this is what we're calling the critical speed, or you could also say critical velocity. And what the r refers to, if you're being careful here, is it's the path of the center of mass of the ball. It's that radius. So it would be this radius right here, the path of that center of mass of the ball. So if I were to measure this radius, that would be the one I want. So this is really r path. So the r here, I'm going to call r path. Okay, so that's the theoretical equation for the critical speed. It's simply going to be the square root of the radius, again, which means the radius of the path of the center mass of the ball, times g. In this case, by the way, this would be the path, right? Since it's rolling underneath. Okay, so let's go back to the handout. So again, I talked about the centripetal acceleration, right? We talked about the magnitude being v squared over r, or we could write it as omega squared r. Then we talked about centripetal force, right? Again, it's the force that's directed towards the center, and it's simply equal to ma, where the a is the centripetal acceleration. So it's either going to be mv squared over r or m omega squared r, depending on whether we want to use this linear velocity, right, which is also called the tangential velocity, or if we want to use the angular velocity or angular speed. We talked about the situation where the ball is rolling over the roller coaster track and then under the loop, and we derived the critical speed, right, when the ball is just ready to lose contact at that highest point, either just ready to jump off the roller coaster track or to fall off the loop. And that critical speed ends up being the square root of g times r, where the r here is the path of the center of mass of the ball. Okay, so for the first experiment, and again, this deals with this rotational apparatus, make sure you watch the short little video that I created where I describe how I actually collected the data. Basically, what you have going on here is you have this hanging object, and it's going to be rotated around in a circle. So this thing rotates around. Again, this will make more sense if you watch this video. And you're going to rotate it at a certain speed, a certain angular speed, so a certain omega, such that the hanging object hangs vertically. Okay, and then what keeps it going in a circle? So if you were to look from above, you would see its circular motion. It's going to be the tension in the string here. By the way, when you do that part, this string is not attached. So you have to kind of ignore this part. This is going to be the second step when we want to find the centripetal force experimental. So ignoring this piece right now. So it's just the hanging mass here. It's hanging from, hanging object here. It's hanging from a string. It has a weight. Those two forces are going to add to zero, right, when it's vertical. So the only force that's acting is going to be this force, the tension in the string that's pulling towards the center. And that's going to be the centripetal force that we're trying to calculate, okay, when it's rotating around. Okay, here's some information. The radius is 0.15 meters. So this post right here is 0.15 meters away from the center, or when the hanging object is hanging vertically, its center is exactly 0.15 meters away from the center. So that's the radius as it rotates around. I give you the mass of the hanging object. That's 0.2075. Remember, that's the thing that's being rotated, the hanging object. And then this you'll need later. The hanging mass here is that blue weight set, what we had to add to the hanger here, so that this whole thing is balanced and the hanging object is hanging vertically. And that ends up being 0.0700. Okay, so the first thing that you do Let me describe like where this comes from. So we want to calculate the centripetal force here, the tension in the string, both experimentally and theoretically. Experimentally, what we do is exactly this setup right here. We have another string on the left-hand side, which goes over a pulley and connects to this hanging mass. And then I put weights on the hanging mass such that this hanging object is completely vertical. It's just hanging vertically. So now we know that the tension on this side must equal the tension on this side. And I can easily calculate the tension on this side because the pulley here just redistributes that tension. So the tension pulling up, right, is the same as the tension pulling out. And I know if I look at this hanging mass, I have two forces. I have the tension pulling up and I have the weight pulling down, right? So it's going to be mg would be the weight. So since this is not accelerating in the vertical direction, that tension in the string must equal the weight of the hanging mass. So ultimately, the weight of the hanging mass is going to be your centripetal force here. It's sort of our estimate of the centripetal force experimentally. Okay, so all I did was I collected or I put on, a particular mass there such that this was hanging vertically. So that's given in the table here. So it's 0.0700 kilograms. All right, later you're going to have to calculate the experimental centripetal force, but that's simply going to be this mass times g, right, times 9.8. Okay, now, again, you have to watch the video to see how I did all this. Now this string is taken off, and the hanging object will like swing up a little bit, but when you start it spinning, it'll go back down until it reaches the vertical position. And we know that because there's like a little orange indicator here that lines up with the bracket. So I know it's hanging exactly vertically. And what I'm measuring is what that omega is, what that angular speed is, such that this hangs vertically. So if you look at this table here, I did 10 trials, and this is the angular speed. So this is omega for each of those trials. And it's in radians per second. So 4.68 radians per second, 4.63 radians per second, and so on. Okay, so question one, all I want you guys to do is to compute the average omega, so the average angular speed. Make sure you round to two places, right? That's the resolution of the instrument, is 0.01 radians per second. So round to two places. And then also calculate the percent experimental accuracy. So again, you have to find, right, we reviewed all this in lab 0. You have to find all the absolute deviations, how far each value is away from your average, then average them, make sure you round to two places. And then of course the accuracy is going to be the average absolute deviation divided by your average angular speed times 100. Once you have that information, so once you have omega here, now you can compute the centripetal force theory. So this is our like theoretical value of that centripetal force. So remember, it's going to be m times the centripetal acceleration, which we're going to use the one involving omega. So it's m times r times omega squared. The m here is the thing being spun around. It's the mass of the hanging object, right? So the m here is the 0.2075. It's this thing that's being spun around. The r was given, right? The radius, 0.15, and then you can use your average omega for your omega here. Okay, so that will be the centripetal force theory. Okay, then I want you to estimate the percent experimental accuracy for the centripetal force theory. Well, remember, to do that, if you have an equation that involves multiplying several quantities together, then the rule is if you want to find the percent experimental accuracy for this dependent variable, the centripetal force, you have to add these respective percent accuracies. And since omega is squared, you have to add it twice, right? So it would be the percent experimental accuracy for mass plus the accuracy for radius plus the accuracy of the omega, and you have to add that twice for omega. So for omega, we already have, right? You calculated it. So you have that value here. That's the percent experimental accuracy for omega. How do you find the percent experimental accuracy for mass and the radius? We're going to estimate it by using the resolution of the instrument because we're only measuring the mass once and R1. So we're just going to estimate it. So remember the scale, its resolution was 0.1 grams, which is 0.0001 kilograms. So to estimate the percent experimental accuracy for the mass, it's going to be 0.0001 divided by the mass of the hanging object, right? The 0.2075 times 100. So that'll be the accuracy for the mass. The accuracy for the radius is going to be 0.001, that's the accuracy of the instrument, divided by 0.15 times 100. And I have the final equation written here. If you want the accuracy for the centripetal force, it's the accuracy for the mass plus the accuracy for the radius, plus you have to add the accuracy for the omega twice, or you can just multiply by 2. Okay, so that'll be the percent experimental accuracy for your centripetal force theory. Okay, question 3. Compute the experimental value of the centripetal force. But that's just the weight of the hanging mass. And you have to be careful with these terminology, right? Hanging object is the one that's being spun around. Hanging mass is like blue mass set that you hung so that this balanced earlier. So if you compute the weight, we know the mass. If you multiply by 9.8, that'll be the weight of the hanging mass. That's going to be your experimental centripetal force. Okay, and that will go in here. This theory one, you can also write in here in this table. So question 4, I want you to compare these two. Hopefully they're fairly close by computing percent experimental error. Okay, make sure you show me all these calculations as well. Okay, question 5. How does the centripetal force vary with the angular speed for a constant radius of the circular path? I.e., is the relation linear, quadratic, cubic, inverse square, etc. So if you look at this equation, actually here, let me do this part on the iPad. Okay, so remember the formula for the centripetal force was m times r omega squared. And this question asked, how does the centripetal force depend on the angular speed if you have a constant radius? Okay, so the way to think about this, right? We know the mass is constant, right? The hanging object, that mass doesn't change. And if we're saying the radius is constant, then we know that these two variables multiplied together are just going to be another constant. Let me call it k. So the centripetal force is going to be some constant times omega squared. So another way of saying this is you can say the centripetal force is dependent on omega, right? It's a function of omega. So the question is, what type of function is that? Is that a linear function in terms of omega? Is it quadratic? Is it cubic? Is it inverse square, etc.? Okay, so I'll let you guys think about that. And then the next question was assume that, so I'll start with the same formula here. Assume that now the angular speed is constant. How does the centripetal force depend on the radius? So the way to think about that now is if this, right, if that product is constant, I can think of this as it's a constant times r. So now it's really like a function of the radius. And what type of function is that? So if you guys remember, your pre-calculus or college algebra, what type of function is that? If it's like r, think of the exponent will tell you the answer, right? In this case, it's like a 1 here. Is it linear, quadratic, cubic, inverse square? What type of relationship is that? So that's all really that question, those two questions are asking. Okay, so next part B, this is the roller coaster track and the loop track part. So again, I recorded a short video showing how I collected the data. So you want to make sure you watch that video. That's really important to watch it. And basically the ball starts at the peg here. It's going to roll down. And I have it set up so it's just ready to leave the surface right at point P. And I have a photo gate set up there. So there's a photo gate right at point P. So in this first table, what I did was I collected the time it took the ball, so think of it as like the diameter of the ball, that steel ball, to pass through the photo gate, right, which was at point P. And these are the I did 10 trials. These are the 10 times I got. Okay, so question 7 is I want you to compute the average time that it took the ball to pass through the photo gate. Make sure you round to 4 decimal places. And then also compute the percent experimental accuracy for that time. Okay, then question 8, determine the average linear speed at position P. So determine the velocity at position P. And we're going to call that our experimental velocity. And we know that that is really our critical speed, right? Because it's set up so that the ball is just ready to leave the surface at point P. So how do we find that critical speed experimentally? Well, this is similar to what we did, if you guys remember way back. Actually, we did a couple of experiments like this, but in particular, the ball drop experiment, right? When we measured the acceleration due to gravity, we had to measure the velocity of the ball at photo gate A and the velocity at photo gate B. And to do that, we use the fact that the average velocity is displacement divided by time. And the displacement is really just the diameter of the ball, right? So same thing here. If we take the diameter of the ball divided by the time it takes to pass through the photo gate, that's going to be an estimate of our velocity at that point. And that is really our critical speed. It's our experimental critical speed. So the diameter of the ball is given. Remember, it's 1.90 centimeters, but in terms of meters, we want everything in SI units. It's 0.0190 meters divided by, you're just going to divide by your average time. And that will be your experimental critical speed. Okay, question 9. Now we want to calculate the critical speed theoretically, right? But to do that, remember, we need the radius of the path of the ball. So what I did was I took off that roller coaster track and the loop track, and I kind of sketched out the circular part of the track, and I measured the radius of that circle. So the radius of that circle is called, I call it R trace. Think of it, I traced out the track itself, assumed it was a circle, measured the radius, and that's R trace. But what we really want for our formula is our path, right? The path of the center of mass of the ball as it rolls over the surface. So how do I find R path if I know R trace? Well, it's almost equal to R trace. I have to add one little thing. What do I need to add? Well, I need to add the radius of the ball, right? It's the radius of the trace plus the radius of the ball. That will be R path, at least for the roller coaster when it's rolling on top. So our path for the roller coaster track is going to be R trace plus R ball. Okay, so I gave you the information in the table here so you can find our path. And then finally, question 10, now we can calculate the critical speed predicted or theoretical by using the equation. It's going to be the square root of g times R path. Right, in g, you can just use 9.8. Okay, now you want to compare. So the other part of question 10 is compare your predicted or theoretical critical speed to the experimental critical speed that you got from question 8 by computing the usual percent experimental error. And make sure you show me that calculation. Okay, part C, exact same thing, right? Same set of questions, except now we're dealing with a loop, right? So now it's rolling underneath. So again, I collected the time. I had a photo gate there that was installed. It was upside down now, the photo gate. And I collected the time it took the ball to pass through that photo gate for 10 trials. So these are my 10 values. So question 11 is compute the average time and compute the percent experimental accuracy. Question 12, determine the experimental critical speed, right? So the linear speed at position P, again, by using the diameter of the ball divided by the average time. So now this average time here in this table. Question 13, determine the radius of the path of the ball, but now it's rolling underneath, right? Because it's a loop. So now the R path is going to be the trace of the loop, the radius of the trace, right? When I sketched it out and I figured out the radius of that circle, minus the radius of the ball, right? That'll be our path. So compute that. And then question 14 is compute the predicted or theoretical critical speed by using that equation. And then compare it again to the experimental critical speed that you found from question 12 here. and then how do you compare them? The usual, we're going to compute the percent experimental error. And make sure you show me all these calculations, right? Show me the calculation for our path, show me the calculation for the critical speed predicted, and show me the calculation for the percent experimental error. Okay, so that's it for the circular motion part. The second experiment is going to deal with, again, we're going to look a little bit at moment of inertia and conservation of angular momentum. Okay, so first, a few things I need to define here. A rigid body, you can think of as any object, right, in which the atoms or the pieces of the object that make up the object are in fixed positions relative to one another. In other words, they don't move at all, right? So think like any solid object would be considered a rigid body. Okay, so that's the first definition. Moment of inertia. What is moment of inertia? Well, if I have some object here and I break it up into little bits of mass, right? So M1 is here, M2 is here, M3 is here, M4, M5. You break this whole thing up into little bits of mass all the way through Mn. I'm just showing 4 of them right now. And each little bit of mass is a certain distance away from the rotation point, the point at which you want to compute the moment of inertia about, right? Because it depends on what point you choose. So in this case, we're choosing this point right here. So M1 is R1 away from that point. M2 is R2 away. This is like its radius from that point. M3 is R3 away, and so on and so forth, all the way up to Mn, which is Rn away. Well, then the moment of inertia is defined to be the sum of each mass times its distance squared from the rotation point. Okay, let me jump on the iPad for a second to explain this a little bit further. Okay, so again, let's say we have this object. Let's say the axis of rotation we're going to choose, and we can choose any point we want to calculate the moment of inertia about. Let's say we choose this point right here as axis rotation. Then I can break this object up into little bits of mass. Like this is say M1, then let's say M2, M3, and so on, M4, all the way up to Mn. And each little bit of mass is a certain distance away from the rotation point, from the axis of rotation. I'll call this R1. This is R2. This is R3. This one would be R4, Rn. Okay, and again, you have to imagine that the whole thing is broken up into little bits of mass. And then if I want to compute the moment of inertia, which we call I, then this is simply going to be equal to M1 times R1 plus M2 times R2 squared plus, sorry, the radius is squared, plus M3 times R3 squared plus dot, dot, dot. And then you go all the way to the last one, which I'm calling Mn times Rn squared. But a more efficient way of writing this, since I'm summing all those things, I can write a sigma, right? It means sum. And the index goes from 1, so I equals 1 to n. And I can write this as MIRI squared. Okay, and then it has units, right? The moment inertia has units. Since it's a mass times the radius squared, it's going to be kilograms times meters squared. So the moment of inertia depends on the distribution of the mass about the point of rotation. Okay, so it depends on the distribution of the mass about the point of rotation. Here's an example. Let's say we have a ping pong paddle. So something like this. And so same paddle, right? So they have exactly the same mass. wasn't drawn very well, but assume it's exactly the same shape, right? Same paddle. So same mass, but in this case, I calculate the moment inertia about this point in the handle. In this case, I calculate it about this point in the paddle itself. So for which case would I have a larger moment of inertia? Again, they have the same exact mass. It's just that the mass is distributed differently depending on what I choose as my axis of rotation. Well, hopefully you guys can see in this left-hand case, see how the mass is further away from that rotation point? And remember, to calculate moment inertia, I'm using each little bit of mass times its distance squared, right, from the point of rotation. So if the mass is further away, that's going to lead to a larger moment of inertia, where in this case, the mass is closer to the rotation point. So I'm going to have a smaller moment of inertia. So I'll call this I1. In this case, I1 is going to be greater than I2. Okay, so it depends really on the distribution of mass about the point of rotation. Okay, another way to think about moment of inertia is we can look at Newton's second law. And in particular, we're going to look at Newton's second law defined for rotations. So I'll say for rotations. So first of all, let me do Newton's second law if we have a particle, right? Remember, that's F net is equal to mass times acceleration, right? F equals ma. Net force equals mass times acceleration. Well, it turns out there's an analogous formula that you guys will talk a lot about in lecture. You're going to learn about this in lecture, where there's an analogous term for force, for the net force. And you may already know this. It's called the torque. So we have the net torque is equal to, there's an analogous term for the acceleration. Instead of linear acceleration, we have what's called the angular acceleration, alpha. So net torque is kind of like your net force, but for rotations. Alpha is kind of like your A, right? Angular acceleration is like linear acceleration, but for rotations. So you might imagine there's something analogous to mass, but for rotations, and there is, and it is the moment of inertia. So I is analogous to mass. So it's kind of like, you can think of I as like a rotational mass. I'll say acts like a rotational mass. Whereas mass resists changes in linear motion, right? If you have a larger mass, it's harder to accelerate the object. A larger I is going to resist changes in angular motion, right? So if you have a larger I, it's harder to angularly accelerate. It's harder to rotate an object if you have a larger I. So resist changes in angular motion. Okay, let me go back to the handout and go over a few more definitions. Okay, so again, we talked about the analogies between rotational form of Newton's second law and the linear translational form of Newton's second law. So this is the one you're most familiar with, right? The sum of the forces, the net force equals ma. And there's an analogous formula saying that the sum of the torques, the net torque, equals I times alpha. So I, again, is sort of like a rotational mass. It resists changes in angular motion. All right, a few more definitions. So actually, let me start with simple pendulum, because we've talked about this in the first semester, right? There's a couple of labs actually where we use a simple pendulum. Remember, a simple pendulum is simply a point mass that's at the end of a lightweight string or a lightweight rod. Okay, and in this lab, we're going to use a washer tied to washer tied to a string. That's going to be our simple pendulum. A physical pendulum is just some rigid body, right? So it can be any rigid body we want. It could be, in this lab, it'll be an aluminum stick. It could be like a baseball bat. It could be something that's just a solid object, right? That hangs from some rotation point, and it can oscillate back and forth. about that rotation point. The period is the time it takes the pendulum to complete one oscillation. Okay, so it turns out that the period of a physical pendulum is given by this formula. So remember, T represents period. It's 2 times pi times the square root of the moment of inertia of that physical pendulum about the point of rotation divided by the mass of the physical pendulum times g times d, where d is the distance from the axis of rotation to the center of mass. And then this one we already know, again, from our first semester, the period of a simple pendulum is simply equal to 2 pi times the square root of the length of the simple pendulum divided by g, right? It only depends on the length of the simple pendulum. Okay, so why am I mentioning all this? Well, we're going to use these ideas of the period of a pendulum and a simple pendulum to solve for the moment of inertia of that aluminum stick about certain points of rotation, about its axis of rotation. So we're going to use these ideas. How do we do that? Well, first, we have to know there's another term here. It's called an equivalent simple pendulum. This is simply a simple pendulum whose length is adjusted so that its period is the same as that of the physical pendulum. And again, if you watch my video, I recorded a quick little video on this showing you how I collected the data. You'll see I adjust the length of that simple pendulum, the length of the washer that's on the string, so that the washer and the aluminum stick oscillate with exactly the same period, right? So then the length of that simple pendulum is now called the equivalent simple pendulum because it has exactly the same period. So we're going to use that idea to solve for the moment of inertia of that aluminum stick. So how do we do that? Well, if they have the same period, right? If the period of the physical pendulum, which is the aluminum stick, is equal to the period of the simple pendulum, the washer on the string, I can set them equal. So here I set these equal. Basically, a little bit of algebra here. You're going to solve for I, solve for the moment of inertia. And you're going to find that I is going to equal the mass of the physical pendulum times d. Remember, that was a distance from the from the axis of rotation to the center of mass, times L, where L is the length of that equivalent simple pendulum. So it's just equal to mdl. So think of this I here as being our experimental moment of inertia. This is how we're going to find the moment of inertia of that aluminum stick experimentally, by using mdl. Okay, and then later, we're going to calculate the moment of inertia of the aluminum stick theoretically by using what's called the parallel axis theorem. So what does the parallel axis theorem say? Well, it says if you know the moment of inertia about the center of mass of the object, right? And I'm going to give you guys the moment of inertia about the center of mass of the aluminum stick. So if you know about any object and you want to calculate the moment of inertia, not about the center of mass, but about some new point, let's say this point right here, which is h away from the center of mass. By the way, h is really equivalent to what d was in the previous examples, but we're just calling it h now. So how do I calculate that new moment of inertia about this new point? Well, it's going to be, so I want I now, the moment of inertia about this new point. So the sub-zero means about this new point. It's going to be the moment of inertia about the center of mass, plus we have to add this an additional term here, which involves h, and simply going to be the mass of the object. So the mass of that physical pendulum, the mass of the aluminum stick, times h squared. So the moment inertia about any new axis is always equal to the moment inertia about the center of mass plus mh squared, right? That's what the parallel axis theorem is saying. We can shift the axis of rotation from the center of mass to some new location if we add this additional term here. Okay, one more piece of terminology for the moment of inertia stuff. There's something called the center of oscillation. And it says for every axis O that a physical pendulum oscillates about with some period, there exists another axis O prime, about which the physical pendulum will oscillate with the same period. And the length of the equivalent simple pendulum defines the location of the center of oscillation from the original axis of rotation. So what this is saying is that we're going to look at the aluminum rod, right? And at first, we're going to rotate it about the end of the aluminum rod. So the axis of rotation is right at the end of the rod. And there's going to be some period, right? It has some period, oscillates back and forth. It turns out there's another location on the rod, and you're going to see this when you watch my little video. There's another hole that's towards the center. It's not exactly in the center, but I call it like a more central hole. And if you hang it from that more central hole, it oscillates, the aluminum stick will oscillate with exactly the same period. So that new location, that new hole is called the center of oscillation. Okay, it's actually like 2/3 of the distance from the end. Actually, here, let me go down and show you a picture of this. So we're going to rotate about the end point right here, right? And it's going to have a certain period. It's going to oscillate back and forth with a certain period. Then it turns out if I, instead of using this point as my axis rotation, I hook it up to this point right here. So you think of it right here. And now this part oscillates back and forth about this point. It'll have exactly the same period as the original one did when it was oscillating about the end. So this new hole, this more central hole here, is called the center of oscillation. Okay, and then the last thing that we want to look at in this lab is a little bit, at least qualitatively, look at angular momentum and conservation of angular momentum. So let me just briefly review what momentum is. And let me start with linear momentum first. So linear momentum of a particle with some mass or an object of mass m. Remember how this is defined, right? We usually call it p for linear momentum, and it's simply equal to the mass of the object times its velocity, right? And it had units of kilograms times meters per second. So that was linear momentum. Well, there's an analogous concept or idea, something called angular momentum. Usually we call it L. It's also a vector. Some books will use H instead of L, but in this case we'll call it L. And we can kind of figure out this equation just by analogy again. If we think about like what's analogous to our linear quantities, but for angular. So what's analogous to linear velocity v, but for angles, it's going to be angular velocity, right? So the v sort of corresponds to our omega, which is really a vector, being careful. And remember the m, what does it correspond to in terms of rotations? It's the moment of inertia, right? So it's going to be I. And it has units of, actually it'll be kilograms times, let's see, I guess it'll be meters squared per second. Okay, now we talked about conservation of linear momentum, right, in the first semester. So remember, one way of writing Newton's second law in terms of linear momentum, we could say the net force was equal to the time rate of change of the total linear momentum. And again, if you haven't seen calculus, remember you could think of this as just as delta P total over delta T. And then the key thing we said, well, if the net force is 0, then that means the change in the total momentum, right, the change in total linear momentum was 0, which meant that the final linear momentum minus the initial linear momentum is equal to 0. And then, of course, we could bring one of those to the other side, and we could say P total final was equal to P total initial. Okay, and that's what we meant by a linear momentum, total linear momentum was conserved. Okay, if the net force is 0, then total linear momentum was conserved. And since this is a vector equation, this could also just hold for one of the components, right? Maybe just the x component or just the y component could be conserved. Well, there's an analogous situation for rotations, right? So instead of F net equals the change in total linear momentum divided by time, we can say that the net torque equals the change in linear momentum. I'll say total linear momentum divided by time. So again, if you don't like the calculus, I'll write it as change in L total divided by delta T. So now we can say if the net torque is 0, then that means the change in the angular momentum is equal to 0. And then we could say that the total angular momentum final, so same argument as before, minus the total angular momentum initial is equal to 0. Or we could say that total angular momentum final is equal to total angular momentum initial. Okay, so it's the same type of reasoning that we use for the linear momentum, except now we're talking about rotations. So instead of a net force, we have a net torque. And if the net torque is 0, then angular momentum is conserved, right? The final angular momentum equals the initial angular momentum. And again, since this is a vector equation, this is true for each of its components. In our case, right, when we have the spinning chair, and you'll see this video when you look at the handout, it's spinning about the vertical axis, right, which I'm going to call the z-axis. So this equation, this conservation of angular momentum, is going to hold when we talk about just about the vertical axis, because that's the only thing that we're really interested in. So if, let me write that here. So in the lab, with the spinning chair, we have that the sum of the torques about the z-axis is equal to 0, right? So there's no torque applied about the vertical axis. Basically, what we're saying is that chair has really good bearings, so there's not a lot of friction. So we're going to assume that the net torque, or the sum of the torques about the vertical axis, is 0. So that means that the angular momentum about the z-axis, about the vertical axis, is conserved. Let's spell this better here. Another way of saying that is my LZ initial, so angular momentum about the vertical axis initial, has to equal my LZ final. And remember, L is I times omega, so I can say like I initial omega initial, that's like my LZ initial, is equal to I final times omega final. And that's really what we're going to use in this lab. And I'm not going to do a lot with this. We're just going to kind of qualitatively talk about this. All right, great. Let me go back to the lab handout now. Okay, so on the iPad, right, I defined angular momentum. Remember, angular momentum, L is I times omega. And then we drew an analogy between conservation of linear momentum and conservation of angular momentum. And we said that for angular momentum, if the sum of the torques is 0, then the angular momentum is conserved. The L initial is equal to L final. And this occurs for any of its components. And really what we're interested in is the angular momentum about the vertical axis is going to be conserved. So I initial omega initial equals I final times omega final about the vertical axis. Okay, so for part A, again, make sure you watch this short video here on how I collected the data. This was the experiment involving the aluminum stick, okay? So first we hung the aluminum stick from the end. So we're gonna calculate the moment inertia about the end first. We hung a simple pendulum, right, consisting of a light string and a washer from the same pivot point, right, from the end. And I adjusted the simple pendulum so that it became an equivalent simple pendulum, and both pendulums oscillated with the same period, right? So they had exactly the same period. And I found that the length of the equivalent simple pendulums when it had the same period was 66 centimeters. I measured its length. The length of the aluminum stick is a meter, so it's 100 centimeters. Okay, so question 15, your first question. Determine the ratio of the length of the simple pendulum to the length of the aluminum stick. The final answer should give the length of the equivalent simple pendulum L in like little l, in terms of the length of the aluminum stick, capital L. For example, if the length of the equivalent pendulum was 72 centimeters and the length of the aluminum stick was 100 centimeters, then little l is going to be 0.72 big L, right? Because you can think of it as, you know, the ratio of little l over large L is equal to 72 over 100. So little l is ultimately going to be 0.72 times big L. In our case, right, and you can see it here, instead of 0.72, what do you think you're going to use? Right, it should be 0.66. So you want to come up with that equation for the length of the equivalent simple pendulum. Okay, question 16. Now we're going to determine the experimental moment of inertia of the aluminum stick about its endpoint. And we're going to use that formula that we derived by setting the periods equal, right, of the physical pendulum, which is the aluminum stick, and the simple pendulum. Remember, the formula we derived was I, this is like I experimental, is the mass of the aluminum stick times D, which is the distance from the rotation point to the center of mass, times little l, which is the length of the equivalent simple pendulum. So we know that it's a uniform aluminum stick. So we know that the center of mass is right in the center. So the D here is going to be the length of that aluminum stick, capital L over 2. And you don't even have to put in any values here. We're going to leave everything in terms of M and L. So capital M and capital L. So you're just going to leave it algebraically in terms of M and L. You don't have to put in 100 centimeters or 1 meter or anything like that. So simply you're going to plug into this formula, right? We have M, D is L over 2, and little l we found from above is going to be, I guess it'll be 0.66 times capital L, right? So you can plug all that in, and that will give you the experimental moment of inertia about the end point. Basically, it's going to be some decimal times ml squared. Okay, when you're finally done, there'll be some decimal times ml squared. Okay, question 17. So now what you do is you change the location of the axis of rotation. So now it's no longer rotating about the end, but now it's going to be rotating about the more central hole, right? Let me show you the picture here. So here was it rotating about the end. Now you're going to rotate about this more central hole. And you're going to find that it has exactly, so this is question 17, you should find that the aluminum stick has exactly the same period when oscillating about this more central hole. Therefore, that more central hole is called the center of oscillation. So now we wanted to determine the moment of inertia, the experimental moment of inertia about the more central hole using the same equation, mdl. So the m is just capital M, just use m. D now is going to be different, right? Because remember, D is a distance from the axis of rotation to the center of mass. So that would be this distance right here. It's called H in the other example, but this is D right now. This is also D. So how do we find that? Well, you're told that the distance of that central hole from this end is 2/3 the length of the aluminum rod. So this is 2/3 L, 2/3 capital L. We know that the distance from the center of mass to this end is half of capital L, right? The length of the aluminum stick. So what is this distance D, which is also called H later on? Well, it must be 2/3 capital L minus 1/2 capital L, right? And that turns out, so 2/3 is the same as 4/6. 1/2 is the same as 3/6. So 4/6 minus 3/6 is 1/6 L. So it's just capital L over 6. That's going to be your D. And I have that right here. So D is L over 6. Okay, and then little l, so D has changed. Little l is the same as what you got from question 15 again, 0.66 capital L. So you're going to write that out. That's going to be your experimental moment of inertia about the more central hole. Okay, question 18. Now we want to calculate the moment of inertia theoretically. And how we're going to do that? We're going to use the parallel axis theorem to do that. So remember, the parallel axis theorem says that the moment of inertia about a particular point, let me go back to the picture here. So the moment of inertia about some new axis of rotation is the moment of inertia about the center of mass. So as if you calculated about the center of mass, and I'll give you that value, plus mh squared, where h is this distance from the center of mass to the new point that you want to calculate the moment of inertia about. So you have to add this mh squared to the moment of inertia about the center of mass. So when we calculate it about the end, right, it's going to be the moment inertia about the center of mass. Well, what is that? I give that here. It's 1/12 ml squared. This basically comes from calculus. If you look this up in a physics book or an engineering book, you'll find that the moment inertia of a thin rod or thin stick about its center is 1/2 ml squared. H is really the same as D from before, right? It's the distance from the center of mass to the new point of rotation. Well, if we want to calculate about the end, then the H here is going to be 1/2 capital L. So now you have to solve for the moment inertia about this new point. It's going to be the moment inertia about the center of mass, 1/12 ml squared, plus m times h squared. So you have to plug in 1/2 L and square it, do a little bit of algebra, and you're going to find that the moment inertia is going to be some fraction times ml squared. Okay, and if you want, you can write that fraction as a decimal ultimately. Okay, then you're going to do the same thing, but now you're going to use the parallel axis theorem to calculate the theoretical moment inertia about the more central hole. So this hole right here. So again, it's the same formula. It'll be the moment inertia about the center of mass, which is 1/12 ml squared, plus mh squared. But h now is going to be the distance from the center of mass to that new axis of rotation. That's going to be L over 6. So you have m times L over 6 squared. You have to square that. You have to add the fractions. And again, ultimately, you're going to come up with some fraction times ml squared. Okay, so here's like the main table. This is the experimental moment inertia about the end. That's from question 16. Again, you're going to have a decimal value times ml squared. Here is the experimental moment inertia about the more central hole. So that's the one from question 17. Again, it's going to be some decimal value times ml squared. These are going to be the theoretical moments of inertia using the parallel axis theorem. So these are both from question 18. Again, about the end and then about the more central hole. So this is going to be some fraction times ml squared. If you want, you can write that fraction as a decimal. And how do you know if you're correct? These values should be very close. When you write it in decimal form, it'll be some decimal times ml squared, and they should be almost identical. And the same thing for these two. You should find that they're very, very close. So question 19 is to compare these two by computing a percent experimental error. So you're comparing the moments of inertia when calculated about the end point experimentally and theoretically. And then you're comparing the moment of inertia when calculated about the more central hole experimentally and theoretically by computing the percent experimental error. Make sure you show me all the calculations, right? That's important. Okay, and then the last part, and again, this is just sort of qualitatively, I don't want to do too much with this. This is the conservation of angular momentum demonstration with the spinning chair, okay? So imagine you have someone sitting in a chair, right? It's able to spin, and you're holding these 2-kilogram weights and you're holding them with your arms out, right? So your arms are out to the side. Someone gives you an initial angular speed, so you're rotating with some omega, right, in radians per second. And then you pull your hands in. So you pull those weights, pull your hands into towards the center of your body. What do you think is going to happen? Do you think you will spin faster, spin slower, or stay the same? Okay, so kind of predict what you think will happen in that situation, and then watch the video. This was recorded when I did this lecture. It was a bunch of years ago now, maybe 7, 8 years ago. And go to the part where the student is doing this experiment where they have the weights in their hand and they pull the weights in. So after watching the video, what did you find? Like, were your predictions correct or were they off? Just give me a couple sentences describing what you observed. Is that what you thought would happen or not based on your previous experience? Okay, question 21. Since angular momentum is conserved about the vertical axis, then we know that the initial angular momentum must equal the final angular momentum about the vertical axis. So I can say I initial, omega initial, remember that's the initial angular momentum, equals I final times omega final. So I want you to solve this for I final. So just algebraically solve this for I final. Just divide both sides by omega final. And you should find that I final is less than I initial. So when you pull your hands in, the moment inertia, right, when you pull your hands in, is smaller than the initial moment inertia when you had your hands out. Does that make sense? So just explain like whether that makes sense or not. Okay, and when you look at this equation, based on what you found on the omegas, you should see that I final is less than I initial. Okay, and then the last part is with the bicycle wheel. So again, you have to watch the video to see this, but originally the student is sitting in the chair and they're not rotating, they're still. The bicycle wheel is spinning. If you're looking from above, it's spinning counterclockwise. So it has an angular momentum that's directed upward, right? So this is the angular momentum of the wheel. So the angular momentum of the system is just due to the wheel initially. And it's going to be the moment of inertia of the wheel times the angular speed of the wheel. That's going to be the angular momentum of the wheel initially. And that's the angular momentum of the entire system. Then what happens is the student rotates the wheel away from them. So they rotate it through some angle theta. And it might be surprising, but you're going to see that the student and the chair are going to start to spin counterclockwise. Okay. So let me jump on the iPad one last time to describe the math behind this. And I just want you to really sort of think about this. Okay, so again, because that chair has very good bearings and low friction, then we can assume that the net torque, or I'll say the sum of the torque about the vertical axis, I call it the z-axis, is 0. That means that the angular momentum about the z-axis is conserved. So if I do the angular momentum about the z-axis initial, that's got to equal the angular momentum about the z-axis final. And initially, the only thing that is spinning is the wheel. So the initial angular momentum is, I'll call it I naught omega naught. So this is the angular momentum due to the wheel. And then after, right, after the person rotates the wheel through some angle theta, it might be easier to draw. Here, let me draw this out a little bit. So this is before they rotate, and then after they rotate the wheel. So initially, the wheel's spinning, and it turns out angular momentum is a vector. It has a direction. And initially, if you curl your hand, your fingers in the direction of the spinning wheel, your thumb points in the direction of the angular momentum vector. And initially, it's just going to be directed upward. So this is like Li in the z axis initially. I'll call it LZ initial. So this is like I naught omega naught in terms of its magnitude. And then after, they're going to rotate, the student rotates it through some angle theta. So this is theta here. The magnitude of the angular momentum of the wheel is still the same. It's still I naught omega naught. But now only part of that vector is in the vertical direction. Remember, we only care about what's happening with the angular momentum about the z-axis in the vertical direction. So what part of it is in the vertical direction? Well, it's this component, if I project that onto here. So now this is going to be I naught omega naught times cosine of the angle theta. But since it's conserved, right, in the vertical direction, there must be another piece, right? There must be another angular momentum of the system that I have to add to that so that I get back the original angular momentum vector. Like this vector plus this vector has to add to this, right? If it's conserved, because it has to be the same. So what is that additional angular momentum of the system? You'll find now that the student and chair are now rotating. So I'm going to call this I S for student, omega S. So now the student and chair have an angular momentum. So if we look at our formula here, initially it's just due to the wheel, right? I naught omega naught. And then finally, it's going to be, part of it will be due to the wheel. So I have to multiply by cosine theta, plus part of it is due to the student in chair. So what we can do now is we can solve this for the angular momentum of the student in chair. So I'm going to solve for this term. And you're going to find that basically I'm just subtracting I naught omega naught cosine theta from both sides. So the angular momentum of the student in chair equals, I'm going to factor out the angular momentum of the wheel. And this is going to be 1 minus cosine of theta. So this is like a key important equation here. So you see that the angular momentum of the student in chair depends on that angle theta, right? If theta is 0, then we know that cosine, so let's say theta was 0. Cosine of 0 is 1, and then 1 minus 1 is 0. So that means the angular momentum of the student in chair is 0 to begin with, right? It's not spinning. The only thing that's spinning is the wheel. But then when you rotate this, so when theta changes, it's going to affect this value right here. It's going to affect the angular momentum of the student in chair. So if we go back to the lab handout, okay, so back to the lab handout, question 22. I just explained all this to you, right? In fact, I even solved the equation for the angular momentum of the student in chair. So I student omega, like I called it IS omega S, right? Remember, it's going to be I naught omega naught times 1 minus cosine theta. So the only thing I want you guys to think about is, for what value of theta does the angular momentum of the student in chair become a maximum? Okay, so think about that. And does this make sense based on what you observed in the video? So when you're watching the video, you'll see pretty clearly like when the student in chair are spinning the fastest. So what theta, what angle did they rotate the wheel through so that they were spinning the fastest? Okay, great. Hopefully that made sense. I know there was a lot of material in this lab. Again, if you guys have questions, please contact me if you have any questions about any of this. Great, thanks.